high efficiency, high gain device above about Ka band. Furthermore, as we think about system architectures going forwards, the ability to reconfigure circuits to handle multiple bands, to have multiple functionalities with the same hardware, is very attractive. And so as a result, if we want to implement compact but yet highly functional circuitry, the ability to reconfigure it is very important, and also allows us to increase the overall hardware efficiency. Taken together, then, these different challenges really suggest that perhaps new design approaches are needed. And it's my opinion that not only new design approaches are needed, but we need new device structures and we need some new materials to make this vision possible. I want to start with just a little bit of an overview of the first of the different concepts that I'd like to suggest, and that is that in a conventional HEMT, which I'm showing here in the top figure, we have a abrupt interface device with a gallium nitride channel. That's the orange. The purple is an AlGaN barrier, and I've just graphed here what the aluminum composition on a cut through the structure would be. The resulting, as a consequence of the polar nature of these materials, this results in a fixed a spike, a delta function of fixed charge at this AlGaN-GaN interface, and that then, those are fixed charges, that then leads to the formation of a 2-deg of mobile charge very close to the barrier. And that's the fundamental operational principle of these conventional HEMTs. An alternative that we've been exploring, and I think is very attractive, is to broaden our search a little bit and not consider only abrupt interfaces, but also consider controllably engineering the details of this interface so that it's not only abrupt, but we also consider, for example, grading. And that's what I've shown here in this picture: a barrier of purple, a graded layer in this blue to orange transition, and then the gallium nitride channel. And so the aluminum composition would have some sort of a profile like this if I took a cut vertically through the device. Because the fixed polarization charge is just given by the negative of the divergence of the polarization vector, such an aluminum composition would result then in a fixed charge distribution of a delta function at the interface due to this discontinuity, a block of charge due to this finite slope, and that then changes very much the shape of the mobile charge distribution in the device, giving rise to a 3D distribution instead of a 2D distribution. That in turn has many implications for the IV characteristics of the devices, the capacitance characteristics of the devices. Less obviously, the E field also gets changed, and the velocity distribution in the devices also changes. And so I really think this is an opportunity for us to reimagine what it means to make a HEMT. Much of what we have done in the nitrides has been imported or inherited from gallium arsenide and indium phosphide, where abrupt hetero interfaces was really the right solution, but those were nonpolar materials. With the opportunity now to leverage polarization, I think we can reimagine this, reconsider this, and use the really the fact that polarization gives us this additional design handle, and we can therefore make devices that we couldn't otherwise have considered. I'd like to just dive into this just in a little bit more detail. These two graphs are essentially replotting what I showed on the last slide, just maybe a little bit larger. But we see that in the conventional device, we get the fixed charge here, and in one of our candidate devices that I'm going to talk a fair amount about today, this is the graded channel device. And you can see that we've redistributed it. And here is just to give you a sense of what the mobile charge distributions look like. If we take these two structures and we do a self-consistent Poisson Schrodinger solution, for the conventional device, we get a 2-deg with a very sharp 2-deg, very close to the interface. And with this structure, with the more distributed fixed charge, we get more of a 3D carrier distribution throughout the device. That has a number of real benefits. The first is that because of the polar nature of gallium nitride, the LO phonons are quite strongly coupled to the carriers, and so it has been found, not by our group but by a group at Ohio State, that in fact the saturation velocity is tightly coupled to the carrier distribution because of this, and as a consequence, the saturation velocity goes down quite quickly as the carrier density goes up. And so by switching to a high density, tightly confined 2-deg, which has a relatively low saturation velocity, to a 3D distribution where we have the same total number of carriers, but they're distributed differently, we can actually get an appreciably higher carrier saturation velocity, and that's something that we can leverage. Furthermore, by distributing the charges differently, we can reshape, for example, what the characteristics of the transfer characteristics are, and change, for example, the shape of the transconductance, shape of the capacitance. And here I show just an example of that. The dashed curves are a transfer curve, ID versus VG over here. Black dashed curves are for a conventional device, and the blue is for one of our graded devices. You can see the transfer curves look about the same, but when I take the derivative and look at the details, you can see that instead of having a peaked GM, which is very typical of a conventional HEMT, we have the ability to tailor this and make it a rather different, much smoother, flatter function, which is potentially quite attractive, at least for some applications. I thought I would maybe just walk through a little bit of how these devices I mean, they're very similar, but they're also rather different. And so it's kind of interesting. So if I look at, here's the transfer curve, same curve I showed you on the last slide. Here's the computed band diagram to go along with it. And if I bias it at this point, basically at threshold, we see that, not much going on here. If I turn the device on a little bit more, get closer to peak GM, you can see that I've turned on the 2DAG in the conventional device. And I've also begun to get carriers in the graded channel device, but you can see it's much broader. Actually, the total number of charges is about the same, a little bit lower maybe, but it's about the same, but it's much more spatially distributed. And then when I turn the device all the way on, you can really start to see the distinction between the formation of a 2DAG in red and the 3D slab here in the graded channel device. Overall, the drain current density is comparable, but because of these difference in shapes, the transconductance changes a lot, and you can also imagine that because of the different distribution of the carriers, the capacitance also changes a lot. And I show here an example of that. This is a simulation of a 50 nanometer gate length device in a structure that's been scaled to work with such a short gate length. And you can see that the conventional device gives me a very peaky GM. Uh, and the graded channel device, somewhat broader, but you can also see here's the capacitance. In the conventional device, it turns on fairly abruptly, right where the GM peaks up. And because of the broader GM, and because it's related, of course, to the charges, the CGS is also much broader. And this gives rise then now to, as we'll see in a little bit, rather different nonlinearity characteristics in the devices. You'll also notice, of course, that the threshold voltage has been shifted more negative in the graded channel device, and this is just because the gate to channel spacing has been increased a little bit because we had to insert this graded layer in the structure, and that causes the VT to shift. Something that's appreciably less obvious is that when you put a graded layer into the structure, the electric field within the device also changes. This was not something I expected initially, but upon looking at it more carefully and digging into it, it is a direct consequence of Poisson's equation. There's nothing magic happening. It's just a recognition that if you spread out the polarization fixed charge, the E fields have to terminate differently, and that results in a lower lateral electric field. Just as a point of reference, I compare here two different E-field profiles. The red is a conventional device with an abrupt interface, and the blue is one of these devices with a 6 nanometer graded layer inserted within it. And we see that the peak electric field has dropped by about 25% or so. And this, I should mention that one of the things that excites me the most about this is that it means that the field has been reduced, but we haven't added a field plate or done anything that would add additional capacitance or additional parasitics to it. It's by re-engineering the heterostructure that we've gotten this reduction in peak electric field. This is, I think, pretty promising to increase the breakdown voltage of the device. Obviously, we could then raise the drain voltage to make it so the peak field came back up again, or alternatively, operate it at the same drain voltage, have this lower peak field for either reduced high field trapping effects, or perhaps improved reliability, or improved noise figure from the reduced carrier heating due to the lower fields. Something else that's maybe less obvious, but it's a direct consequence of the polar nature of gallium nitride, is that because of the LO phonon carrier coupling and the fact that the saturation velocity depends so critically on the local carrier density, we actually see in these graded channel devices that the saturation velocity, actually, excuse me, I misspoke, that the effective velocity of carriers under the channel goes up considerably as a result of the saturation velocity having been improved. And we show here a comparison, again, a simulation, but nonetheless a comparison of a conventional device which gives us a saturation, or I'm sorry, an effective velocity under the channel of about 1 times 10 to the seventh centimeters per second. Whereas in one of the graded channel devices, we get about a 50% boost to about 1.5 times 10 to the 7. And this is a consequence of taking the same number of carriers, but just spreading them out over a larger volume so that their local density is lower. What this does for us from a device perspective is this higher velocity allows us now to get a better, more favorable trade-off in terms of the FT-LG or Fmax LG scaling products, which in turn allows us to get a higher, for example, Johnson figure of merit. We see that we can get about a 30% boost in the Johnson figure of merit by doing this sort of grading, getting us up to about 6.5 terahertz volts. I should say an important thing about all of this stuff is, how well can we model this? I've shown you some TCAD results the last few slides. You might well wonder whether those are correct, whether they, really match experiment. How does that work? Are they truly predictive? And so I think with any TCAD model, question number one really is the model any good? And so I show here just a couple of examples of devices that we've simulated using our framework and how they compare to experiment. The top couple here, this is a paper by Bob Fitch from the U.S. Air Force Labs from quite some time ago in 2015, and his measured data here is shown in blue. Our simulation data is shown in the black dashed curves for the exact same structure. This device happens to have a field plate and doesn't have any compositional grading. It's in a conventional algan-gan hemp. And in addition to this DC agreement, I'm not showing it here, but we also found that our predictions of FT and Fmax also are quite consistent with his. We've also done a fair number of comparisons with graded channel devices. Here's a device cartoon from HRL, and the blue curves are Jung Sung Moon's measured results from his IMS paper in 2019, and the black dashed curves are our simulation results. Again, showing pretty good agreement. And while this is DC, we also see that our FT and our Fmax also agree quite well. A word about the simulations that we do. We do our work in Synopsys Centaurus. We do have this custom LO Phonon VSAT model that we've coded and added to the base package. The current version, at least as of the 2022 version, Synopsys has also added this functionality in, although I have to say I haven't yet had an opportunity to really verify that it works the same way as ours does. But nonetheless, they're making moves in this direction as well. In addition to that, we also use buffer traps and surface states as deep levels. We don't invent new levels. We just take levels that have been reported in the literature, put them into our device structure. In terms of surface polarization charges, some years ago, one of my students made a bunch of MOS capacitors. We made some extractions of the surface charges. We used those numbers from those experiments in our simulations, and then we didn't adjust any other parameters at all in order to get this level of agreement between experiment and theory. I'm sorry, between experiment and simulation. And so I would say, based on this basis, I think it is now possible to do a pretty good job of predictive simulations in TCAD if one takes a little bit of care with it. So I've shown you some sort of crude basic match. This is the same curve as before. I'd like to just suggest that if we're interested in nonlinearities, subtleties also really matter. And so what I've compared here, for example, is the first derivative of the transconductance and the second derivative of the transconductance, which are really critical features for linearity. And you can see that our TCAD model and the measurements, they don't agree perfectly, but they're certainly in the right ballpark for giving us an idea about even relatively subtle effects like linearity. That's all TCAD and some comparison to experiment. How about real experiment? Can we really see a benefit in experiment from going from an abrupt interface device to a graded channel device? And here's some results that were published by my collaborator and us on exactly that. Here's a conventional algan-gan hemp, and here's a graded channel device. Here's the transfer characteristics, and you can see very much like the TCAD simulations that I showed a minute ago, the conventional device has a rather peaky GM that falls off. The graded channel device is much broader, looks just like our simulations, and also consistent with what we were expecting from simulations. The first and second derivatives of the GM, here's the conventional device, they're fairly large, and they get somewhat smaller when we go to the graded channel device. And also, as I showed in the simulation a few slides ago, the CV curves also pick up a very soft shoulder in the graded channel devices compared to the very abrupt turn on that one expects from a conventional HEMT. So I would say that our TCAD and the measurements that we have so far of experimental devices are really quite consistent. I also mentioned, at least in our simulations, that we expect to see a higher channel velocity because of the lower density of carriers. That is that is actually borne out in an experiment. Is an example of some on-wafer measurements. These are for 50 nanometer gate length devices. And we see here that the red is the conventional Algan GaN HEMT, and the blue is the graded channel device. And you can see that it's not huge, but in FT, you can see there is, in fact, a little bit of a boost in the H21, which corresponds to a little bit of a boost in FT. The FT LG product is actually improved a little bit. And furthermore, you see a bigger difference actually in the maximum available gain, um, which corresponds then to at least maintaining an F max. Um, this is actually maybe a little bit counterintuitive because the gate to channel distance is a little bit bigger in the graded channel devices compared to the scaled HEMPs. And so you might say, well, the electrostatics of the gate are not as good, and that's true. But despite the fact that the gate electrostatics are not as good, the FT and the F max actually improve a little bit, and that's because of the higher velocity making up for the difference in the electrostatic coupling. Give you a sense of the performance over bias, I show here, these are measured FT and Fmax contours for a graded channel device. I don't have the equivalent measured data here for a conventional device, but what you can really see about this is that we get quite high speed over a very large range of drain voltages and at relatively modest drain current densities. And we also get high Fmax over the same bias range as we get high FT. So we've got a very large sweet spot in terms of FT and Fmax that fortuitously occurs at relatively low drain current densities. So this means that I can get very high performance out of something that doesn't burn a lot of power while it's operating like this. And this is in contrast to a conventional HEMT, where typically the highest speed is taken at the highest drain voltage possible. Here we see that the compromise is really quite different. Something that I mentioned before, and I showed a simulation showing you the peak E fields, is that we expect in the graded channel device, based on our simulations, to see some symptoms of a lower peak E field. Actually, we see that experimentally as well. I show here a comparison of the measured noise figure in these devices. The black is the minimum noise figure for a conventional HEMT, and the blue and red are the minimum noise figure for a graded channel device. The blue and the red are just at two different bias points for that device. And you can see that the noise figure is actually improved by about a quarter dB or something like that. Um, First off, the noise figure is extraordinarily low, up to about 30 gigahertz. The noise figure is half a dB or less. But I think more interestingly, it actually tracks really well this reduction in the peak electric field. If you use Werner Bachtold's estimate for the drain carrier temperature, which I've just duplicated here, and in this case, E is the peak electric field within the device, and EC is the critical electric field in the device for the material. This reduction by about a quarter of a dB in noise figure actually tracks the 25% reduction in peak electric field almost exactly. And so this is really a measure directly of the peak electric field within the device. And by going to a graded channel device, lowering the peak electric field, we also get an improvement in the noise figure. And just as an aside, if one wanted to use such a device in an LNA, we would see that in fact you can get this really excellent noise figure to quite low current densities for a very highly power efficient LNA. I'd like to talk a little bit about linearity. I mentioned before that some of the subtleties are rather interesting in this, and we've spent a lot of time looking at it, and so I thought I'd like to share it with you. For linearity, what's really kind of interesting about that, at least from my perspective, is that it depends so critically on relatively subtle changes, and in particular, I would say the device community maybe over focuses on GM. You'll often hear people talk about how flat GM is very important. And GM is very important, but there's other things that go into it. The output conductance is also critical. The gate to source capacitance is very critical. The gate to drain capacitance is very critical. All of those factor into linearity. It isn't just GM. And so in an RF amplifier, you really can't just focus on GM. The key dependencies is really that the source impedance is important because that impacts the noise figure and the gain. And that also, depending on how reactive it is, it changes how large the voltage swing is at a given power level. In addition, the load impedance sets the gain, as well as has a big impact on the overall linearity, for example, through harmonic terminations, and as well as setting up feedback through CGD. And the output voltage in the current swing introduces CGD and output conductance dependencies. And this is where the focus that folks sometimes have on transconductance kind of misses the boat a little bit, because when one measures transconductance, of course, VD is held constant, but in an amplifier, VD is swinging around in response to the input signal. So the transconductance measurement is really not a complete picture. If one does a Volterra series analysis on one of these devices, the formula is truly terrible. If one then takes the Volterra series analysis and does a lot of simplifications, and I'm thankful to Bob Manazian for many years ago for doing this for us, you can get a much simpler equation. This is still plenty complicated, but this is a appreciable simplification from the full Volterra analysis. And you can begin to see what the different combinations and permutations are that go into making the nonlinearity what it is. And just a note on this terminology: GM1 is the GM of the device, GM2 is the first derivative of the transconductance, GM3 is the second derivative of the transconductance. And you can see, for example, there's basically the output conductances, the transconductances, the capacitances, and all of their derivatives that factor into this equation for the intermodulation ratio. If we take that formula, and I don't want to drag you through all of the math, but if we take that formula and we just take a conventional HEMT and we extract all of these terms, we did this for one of the HRL devices, we find that the dominant nonlinearity is in fact the second derivative of the transconductance divided by the first by the transconductance. But that's not the only contributor. That's about half of the overall nonlinear contributions. The other major contributors, there are two slices here, the gray and the orange, that are from the first derivative of the output conductance and the first derivative of times the first derivative of the transconductance. And about 8% of it is due to that's this red one here, is due to the second derivative of the gate capacitance. And so that's for a conventional abrupt interface device. A graded channel device substantially reduces all of these derivatives, and so gives us an opportunity to really improve the linearity without making the power consumption much worse. I'd like to show you that experimentally here. These are experimental measurements taken on these two devices that I showed you previously from HRL. Um, they were fabricated in the same process flow. They had 45 nanometer gate lengths. And what we see is when we do a two-tone intermodulation measurement, first of all, here are the fundamental tones. The black is the conventional device. The blue is the graded channel device for the fundamental. And then when we look at the third order intermodulation, here are the intermodulation spur amplitudes for the conventional device, and those drop by about 24 dB when we go to the graded channel device. Overall, we see that we don't change the gain very much. You can see that these are practically coincident with each other. And the output power is preserved, but the output third order intercept is improved by about 10 dB as a consequence of the 24 dB reduction in the intermodulation products. That then gives us a linearity figure of merit, which we define anyway as the output third order intercept divided by the DC power that's consumed by the device of between 17 and 20 dB, whereas most other devices, it's more like 10 dB or something like that at best. In terms of where do these improvements come from? Well, we took that same formula, the Volterra analysis simplified, and looked at the different pieces. And this is the same pie chart that I had shown you previously for a conventional device. And so here, I've just tried to make this into a bar graph to make it a little bit easier to understand how does it change when I go from a conventional to a graded device. Well, the 48%, that's the red bar here. When I move to the graded channel device, I'm actually able to reduce the second derivative by so much that it goes from this bar graph to this. So it improves by about 25 dB. The other two next contributions, that come from the first order derivative of GM and the first derivative of the output conductance, that's this graph in the conventional. Those practically drop to zero in the graded channel device. The second derivative of the gate capacitance also drops considerably. So when I go to the graded channel device, it drops considerably. But there's never a free lunch. And we can see that this term, the GM squared times the second derivative of the output conductance, actually gets a little bit worse in the graded channel device. And so this is now the limiting nonlinearity in the graded channel device. You can see that this is the biggest thing left. These are all now smaller than that. And so it really tells you that as you make changes to the device to improve the linearity, the notion that the transconductance is the most important thing actually can go away, and it can become something else. And in this case, for example, we're limited by the output conductance. And that's maybe not so surprising. By inserting that graded layer in there, we're actually increasing the gate to channel spacing, which of course makes the output conductance a little bit worse, and therefore makes the derivatives of the output conductance a little bit worse, and therefore the linearity a little bit that becomes the limiting factor in the linearity in an amplifier. In terms of the large signal performance, this is some more measured data. This is 30 gigahertz, a two-tone measurement with 10 megahertz spacings. And you can see this is only for a graded channel device. We find that we can get pretty good gain. We can get quite good PAE at 30 gigahertz, about 60% in this case. And if we saturate the amplifier, we operate clear out here, we see that the carrier to intermodulation ratio is about 17 dBc. However, if we back it off even a little bit, and in this case, back off to, let's say, 6 dB back off, we still get a PAE of about 50% while maintaining a carrier to intermodulation ratio of better than 30 dB. This is the raw device performance. No DPD was used, but yet we get really extraordinary linearity out of these devices. And I think this is especially important as we make the transition to wider and wider communication bandwidths. Doing DPD on very wide channel bandwidth is very, very computationally expensive and very power hungry. Using a device like this that has much better intrinsic linearity may allow us to get away with using simpler DPD, particularly for wide channel bandwidths. I'd like to also talk about the efficiency a little bit. That was just one example. We find that you can, by optimizing things just a little bit, get even better performance that I've just shown you. In particular, we've seen, for example, that you can get peak PAEs of 72%. And in fact, if you go to even lower power densities, you can get peak PAEs approaching the theoretical limit of 78.5% in these devices. And they maintain their advantage and are competitive with even the very best nitrogen polar devices. The real thing with the nitrogen polar is that while the efficiency is maybe not as high, they can go out to higher power densities. And we're still trying to work on how we can improve the power density of these devices. One of the things that I think is really interesting about these devices is that because of the internal field management, we can go to higher voltages than you might otherwise expect before we need to use a field plate. I'd like to focus in on this graph here in the middle. If we take so the black dots are a well field plated Ka band device as sort of a reference of this is about as good as you can do. And it does seem to be that that's pretty close. If you take these an aggressively scaled AlGaN-GaN epi layer and you just put a T-gate on it, no field plate, this is the sort of load pull results that we typically get. If we go to the graded structure, this is the sort of load pull results that we get, and you can see appreciably better power scaling. If we then add a little bit of a mini field plate, just a small one, not very big, 50 nanometers or so of overhang, we can now get, with the graded channel, a device like with it scales like this, like the blue curves. And so as a consequence, what we've got now is a device that looks like it's got a field plate, but doesn't. In terms of, so the power scaling looks as good as a field plated device. But if you then compare the FT that you get, this is the blue. So these devices here represent these devices here. This full field plated device, though, is that one. And so there's a tremendous difference in the FT. These devices are much, much faster. And so because we haven't had to add a field plate, but yet they load pull as if they, just as well as one that does have a field plate. And so this really gives us now a path to getting to high efficiency, high power at even higher frequencies than 30 gigahertz. I'd like to talk a little bit then about what the power implications are. This is actually the same graph, just redrawn a little bit as I just showed you. But I showed you before that by going to a graded channel, we could reduce the peak field by about 25%. That doesn't sound like such a big deal, 25%, but it's more significant than it sounds, because not only is the peak field reduced, but actually the shape of the field is changed, and it results in a dramatic increase in the breakdown voltage. And this just gives you a sense of it. If we simulate the breakdown voltage of the device, conventional device in red and our graded channel device here in blue, this represents the 25% reduction in peak field, but the actual breakdown voltage nearly doubles. And so that is really significant for getting improved RF power scaling. And this has been consistent with our experimental results as well. I mentioned before that this provides a path to 94 gigahertz. Here is the sort of the first results that I'm aware of that show that this is really true experimentally. This is for 50 nanometer gate length devices, and with a little bit of an overhang. You can see here the little 50 nanometer field plate overhang. Um, these devices had a peak PAE at about 50% at the device level, 2 watts per millimeter, and a saturated power up to almost 3 watts per millimeter. And it was enabled by the fact that we can increase the drain voltage well beyond what you could do otherwise with a conventional device, because of the grading. And so far as I know, this is a record for the PAE in the 3 nitride devices, including nitrogen polar. This is a comparison. Here's some nitrogen polar device results, about 30% PAE, and here's our devices here in the open circles approaching 50%. So I'd like to switch gears then a little bit in the time that I've got remaining, and talk about another application, which is that for reconfigurability, we'd like to have really good switches. And I've shown here a hybrid beamformer. This is a hybrid beamformer architecture that was put forward by a couple of people at Corvo a few years ago. And you can see that really the key functions at millimeter wave are, of course, there's lots of stuff. You have to have amplifiers, phase shifters, mixers, all of that. But switches show up actually quite a lot in these devices, in the front end, in the beamformer. And so it's really essential to have a really good switch if I want to make a reconfigurable front end. And in particular, you might imagine that, of course, I can make a power amplifier out of GaN. I showed you a few slides ago that you can make really quite a good LNA out of GaN. If I could also make a really good switch out of GaN, I could make a fully monolithically integrated gallium nitride front end, and that'd be very attractive. So what are we looking at? Well, one of the things we did was we took a look at the limitations of conventional FET-based switches. And there's really a very fundamental trade-off between the on resistance and the off-state capacitance, which leads to the standard figure of merit for a switch of 1 over 2 pi R on C off. And FETs are just sort of constrained by this. Have been some really interesting results, particularly out of Northrop Grumman, but also a few other places where they've used multiple stacked channels to improve this trade-off. But those devices aren't really monolithically integratable with conventional LNAs or conventional PA designs. And furthermore, linearity is still pretty important. And if you've got a switch and you put large signals on it, they can modulate the channel and give distortion just from the switch, not even from the amplifier. And something that we don't often think about as device people, but when you put it into a circuit, in many instances, the gate control line requires a choke or a quarter wave transformer or something else like that that can use quite a large area as well as limit the bandwidth. What we've been looking at in my group is can we do something from a materials perspective to try to make this situation better? And it's my view that ferroelectric gate stacks provide an alternative to make a better switch. Essentially, what this amounts to is using polarization engineering not only in the heterostructure of the device, but also in the gate stack and the dielectric as well. And so I show here two band diagrams for an algan GaN HEMT with a hafnium zirconium oxide gate stack, but the hafnium zirconium oxide is ferroelectric and can be poled in 2 directions. And I just showed the band diagram for each of the 2 directions, and you can see that when poled this way, the device is on, and when poled this way, the device is off. But the gate bias is exactly the same in the 2 cases. So it's sort of got memory built into it. And we're using essentially the PE polarization E field hysteresis to make the FET bistable That improves the intermodulation distortion as well as making the switch more the switch performance a little bit better. Something that we didn't expect, which turned out to be quite favorable, is that hafnium zirconium oxide, at least the way we're depositing it, turns out to be have significant frequency dispersion. I show here the capacitance of the HZO film as a function of frequency, and at low frequencies, it's a high K, like one expects, but at relatively modest frequencies, it starts to roll off. And by the time we get into the millimeter wave range, it's got quite a low permittivity. And as a consequence, what this does is it separates the off-state capacitance from the on-state resistance and improves the millimeter wave performance. Show you here just some examples of what the material properties are. This is for a metal insulator, metal capacitor, the PE loop of the hafnium zirconium oxide. We deposit ours by atomic layer deposition, and you can see that we get very nice hysteresis loops. When we put it into the gate stack of a conventional algan GaN HEMT, this ferroelectric loop actually shows up as a loop in the transfer characteristics. Something I would like to point out is that often when you see loops that look like this in a GaN HEMT, you immediately think it must be traps. And that's probably the right first guess. But we see that actually the sense of the rotation here is not consistent with traps. The hysteresis loop would go the other way if it was traps. This is a ferroelectric loop that's causing this. We then make RF measurements of these devices, and we see that in fact they perform really well. We measured the RFGM, CGS, and CGD from on-wafer measurements, and we see something quite interesting. In a conventional device, the RFGM would be frequency independent. In these devices with hafnium zirconium oxide, we see that they start to roll off at about a gigahertz. But despite the fact that the GM rolls off, the FT is still pretty good at about 50 gigahertz for these devices. And that's because the CGS and the CGD also roll off together with the GM, so that GM over 2 pi CGS plus CGD is actually the same number as it would be if it wasn't any HZO in it. So we're getting the same FT as a conventional device, but because of the lowered GM and the lowered CGS and CGD, we're actually getting much reduced off-state capacitance. But the on-state resistance isn't changed because that's dictated by the DC side of things. And so what that results in then is a much higher figure of merit for the switch. We've tried to understand that in terms of modeling, and I won't go through this too much, but we have done some equivalent circuit modeling of these devices. And what we essentially find is that it's not series resistance limited by the contacts. In fact, there seems to be a series resistance effect internal to the hafnium zirconium oxide. Essentially, the dipoles don't want to switch at a higher frequency, so this resistance is like a resistance to repolarization within the device that causes the permittivity to drop at high frequencies. And the net result then is that we get really pretty good switch performance. I show here, this is measured data on one of our switches. We see the insertion loss here is below 1.5 dB at 30 gigahertz, let's say. The isolation at 30 gigahertz is almost 20 dB. So essentially what we get is out of a single device, we get switch performance that's competitive with many resonant mimics. This doesn't have a choke. This doesn't have any quarter wave transformers. It's just the raw device performance on its own. And so we're already getting switch performance that looks like a mimic. And so if you put this in a mimic, of course, the performance would improve even further. And if we just benchmark against what other folks have reported, this is the result I'm just talking with you now about. We get a figure of merit that's right around 2 terahertz for the switch figure of merit. That is better than, so far as I know, any single channel FET that's been demonstrated in any material system, including GaN, indium phosphide, or silicon. It's directly competitive with the Northrop Grumman stacked channel devices, what they call their slick FET. And the only devices that are really better than it in terms of this figure of merit are 2-terminal insulator metal transition devices, which of course, a 2-terminal device has its own sorts of challenges in terms of system integration. I would say that there's also still plenty of scope to improve this device. These devices had annealed alloyed ohmic contacts. By switching over to a regrown contact, which is something we have started to do, we expect that the R-on can be further improved to improve the figure of merit a bit more. Okay, so with that, I have taken up nearly all of my time, and I thank you for your patience with me. I think I've shown you, at least I hope I've shown you some interesting things. and some opportunities. Certainly, I think it's an exciting time, and I think there's lots of interesting things you could do to improve nitride devices to meet the future needs of systems. And to do so by exploiting fundamental material properties as well as, and one of the things I think is most attractive is polarization grading as a way of really breaking out of this box and getting into a new design space. We've seen that we can significantly improve the linearity, we can significantly improve the noise figure, and we get very good efficiency and power performance. And furthermore, the ferroelectrics are a new material class that we can add to the devices to overall improve, for example, switch performance. With that, those are my prepared remarks. I'd just be happy to answer any questions anyone has.
Yes, we have a lot of questions here. Now,
Fantastic.
first question, Dr. Ma'am. Yeah, ma'am, please come.
Thank you so much, sir, for giving such a deep insight into the device technology. I have just one question. By doing the gradient, by doing the grading, we are saying we are improving breakdown, we are improving everything. But the output conductance should, I think, degrade, as you have also said. And as far as I know, the effective gain you can get out of the device is GM by G naught. So will that not degrade?
Yes, you make an excellent point. That's a very good observation. It is true that so I would say the DC voltage gain, as you say, is GM over G naught. The GM comes down, the GO goes up. So it is true that the open circuit voltage gain in these devices does go down. But what is important to note is that that's not really reflective of the RF gain necessarily, because we will be reactively terminating them. So while the open circuit voltage gain goes down, we find that the actual power gain, the transducer power gain, is not compromised by very much.
Okay, thank you.
Sure.
And any more questions?
About the increase in the saturation velocity with grading.
Ma'am, please come here to ask the question. Yeah.
I just wanted to ask one question regarding the improve in saturation velocity of the carriers with grading. So
Yes.
what is the origin of this, and how will the actual grading affect this improvement? I think you showed linear grading. Is that dependent on how you grade the channel?
Yes, this is an excellent question. The fundamental physics of the saturation velocity is perhaps, how should I say this? People are still arguing a little bit about the fundamentals. I can say that my understanding and my personal view is that this is because of the LO phonon energy in gallium nitride is about 90 MeV. If you make the assumption that as soon as the carriers get that level of kinetic energy, that they immediately scatter and emit an LO phonon, if you make that assumption that scattering is very efficient, then you will wind up getting the VSAT is directly tied to NS, just from a Fermi sphere filling sort of argument. That's the basis for the theory that gives the 1 over square root dependence that I showed you from and that's consistent also with some measurements that were made at Ohio State. So from Siddharth Rajan's group. So that seems to me to be about right. What I would say then is that, so if that's what I believe the physics are. Now, some other folks maybe have argued that there may be other things going on, but I think fundamentally the origin of VSAT versus NS is from this sort of backscattering Fermi sphere filling kind of argument. All right, so then you ask, well, what about the grading? Linear, some other shape? We have shown linear because linear is simple. It was the first thing to do. When you do if you look at different shapes, and we have started to explore that, what that does is that changes then the profile. The NS versus depth can change depending on what sort of grading you do. And that then in turn changes the VSAT. So VSAT's not a constant number in these structures. VSAT is a locally dependent number that changes locally depending on what the local carrier density is. If we change the grading, I will in turn change the local density everywhere and move things around. And so there's a lot of scope here for optimizing that. I can say one of the ones that we think looks the most attractive at the moment is a square root down. And we've done linear. If you take it a little bit different and make it a square root, we get actually a little bit better improvement.
And what about the effect of, say, deep states in the graded layer? For instance, during growth, if we get into some kind of situation where we have deep levels, additional deep levels in the graded channel, so that is also likely to, is it being considered?
That would be bad, right? Deep levels are bad. Right? They're never, deep levels are never a trend. We are fortunately, I think, we have not seen much evidence of that. However, all of the Algan channel that we have done has had compositions of 15% or less. So we haven't really gotten that far away from gallium nitride and haven't seen additional deep levels show up. I think if you got, to very high concentrations, perhaps that situation would change.
Okay, thank you.
I think we have one question in chat box. Yeah.
Oh,
there was one question in chat box.
I can't see that. How do I get there?
Yeah. Yeah. There is one question from Professor Manoj Saxena of Delhi University. Beside the nonlinear transconductance GM, the voltage-dependent capacitances are another source of distortion in gallium nitride HAMTs. Can graded channel HAMT improve AM/PM distortion if used in complementary capacitance cancellation mode?
Yeah, this is an excellent question. We're trying to understand this now, actually. I have one of my students in the lab trying to do load pull in order to understand AM/PM in these devices. We think so. Basically what we see is that the gate capacitance, the second derivative, is dramatically reduced in the graded channel devices. That seems to be consistent with our measurements and our simulations. We think that contributes to improved AM/PM, but we haven't proven that experimentally yet.
Okay, I have one question from my side.
Okay.
Actually, what is the maximum power device, maximum power you have extracted about 30 gigahertz with this 70% peak power added efficiency? This is power density is given. What is the maximum power? Means size of the device for this.
Yes. Let me do some math. Hold on. About half a watt. Oh no, I'm wrong. Hang on. Wait, I forgot. A different device. Hold on. Looks like 800 milliwatts.
Okay.
That was for a 4-finger device, not a particularly large one. We have tended not to make particularly big devices because they're too hard to match in the load pull.
Okay, one more question. So in ferroelectric gate, if we use in our TR modules, so we have to fabricate differently for LNA, power amplifier, everything. Suppose we are using in beamforming network.
Yeah, so the sort of the idea that I had, and obviously we have to see how it works out, but we see with the graded channel device, for example, that we can get a pretty good PA out of the same epi that we get pretty good LNA out of. Adding the hafnium zirconium oxide as part of the gate stack is just an ALD step, and we can add that to some devices and not add it to other devices. So we don't see that as very disruptive in terms of making a switch device with ALD, but next to it an LNA that doesn't have the ALD and a PA in the same epi. So we think we can do it with all the same epi, all the same wafer, and just have the hafnium zirconium oxide only on the switch devices and not on the others. That's the vision.
Okay. Thank you for the answering the question. Any more questions from here? Okay. So now I invite Suchita.
Thank you, Professor Fay, for your informative lecture. I really appreciate the insights you've shared. Now, I request Dr. R.K. Sharma, former Director SPL, to present a memento to our chief guest, DG Med and Cos, Suma Varghese ma'am. Just a token of respect, ma'am.
That's it. Anyway, why? It should have been given to the speaker.
Yeah.
Should be sent to the speaker. Yes.
So Professor Patrick Fay, we have a memento for you also that we will send through post. You will physically receive it.
I'm sorry I'm not there in person.
Yeah, actually, we can show you the memento now. Is it visible? No.
Yes, it is. Oh, yes, it is. Yeah, so every once in a while it shows up and then it disappears. There we go. Yeah. Okay. Oh, that's I'm very flattered. Thank you.
Okay, we will send you, and we'll ensure that you will receive it.
Thank you.
Okay, so we are at the end of our this oration today. It was wonderful talk from your side. So thank you, Professor Patrick, for illuminating talk on state-of-the-art 3-nitride compound semiconductor technology. This is a 3D-dimensional carrier distribution that have flattened the GM and improved the PAE. So we are greatly thankful to you. We are thankful to our DG ma'am, Dr. Suma Varghese, for her vision and giving her time. And Dr. UK Singh, DG Life Sciences. Dr. R.K. Sharma, our former Director SSPL. Dr. Patri, SEMTEM Chairperson, SEMTEM Director, Chairperson, sorry. Dr. Pillai, Director SAG. Dr. Alka Sani, Director PM, for their gracious presence here, and Dr. Meena Mishra, our Director SSPL, for her direction. We are also privileged to have constant guidance of Dr. D.S. Rawal, Scientist H, in organizing this event. As a member of organizing committee, I would like to thank Ms. Suchita Gulati and Mr. Akash Garg for their hard work to make this event successful. I want to acknowledge the help of Dr. Raghavendra Saxena, Ms. Parul Gupta, Muhammad Imran in preparation of invitation cards, and all members of card distribution committee for the invitation. Dr. Sanjay Tomar, Mr. Ashok Kumar, Mr. Anuj for logistics, Mr. Vivek Sharma, Mr. Pankaj Kumar, Mr. Ravi Kumar, Mr. Lovely Gupta, Mr. Neeraj for IT support, Mr. Deepak Vishwakarma, Mr. Pankaj Kumar, Mr. Pradeep, Mr. Shekhar from DITCS, and Mr. Devan Sharma from DPI headquarters to make this event international, that is live on YouTube parallelly. Shri Umakant Goyal, Dr. Sunil Sharma, Mr. Sunil Singh, Mr. Shivnath, and all members of Works and Canteen Committee for venue management and coordination. Thank you all. Now we stand for our Rashtragan National Anthem. नायक जय हे भारत भाग्य विधाता पंजाब सिंध गुजरात मराठा चल जल तिरंगा तब शुभ नामे जागे तब शुभ आशीष मांगे तब जय गाथा जनगण मंगलदायक जय हे भारत भाग्य विधाता जय हे जय हे जय हे जय 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 हे. So now I invite everyone here present in SSPL for cup of tea, and thank you very much for Professor Fay for giving your so early time in the morning and illuminating us in a great. Thank you.
Thank you so much. I'm so indebted to you for the invitation. I enjoyed it immensely. I just wish I was there in person. And thank you to everyone again for the kind invitation.
Okay, thank you.